Hello and welcome to this EE228 video on differential equations. In this video we're going to tackle the first special case that I can think of when trying to solve diffEQs, and that is the case when the homogeneous polynomial has repeated roots, or what they call multiplicity greater than 1. So to address this and show you why it's a problem, let's look at an example case. So the example I want to talk about today is the differential equation y double prime plus 2y prime plus y equals 0. We're just going to look at the homogeneous case. So if we try and get the characteristic equation, we see that there's one double derivative, there are two first derivatives, and there is one zero derivative. So this is the, again, this is the characteristic polynomial, and it factors into lambda plus 1 squared. So this is what I mean by a repeated root. This means that the root r equals -1 occurs twice, right, because of the power 2. So if you said, okay, let's take what we know so far and say the homogeneous solution is a linear combination of exponentials to these roots, you would say this is c1 e to the minus t plus c2 e to the minus 1t. But then you see that these are the same thing, so you might as well just say that's c1 plus c2 e to the minus t. And since we don't know these constants, we don't know their sum, so let's just call that one lumped unknown. So here we see that when the roots are repeated, we can combine those terms in the homogeneous, and they end up being just one term. Okay, that's fine. Nothing terribly wrong with that. We've still got something here for the homogeneous solution. So let's try and solve a diffEQ using it. So let's try and solve the homogeneous differential equation above for, let's say, a couple of initial conditions. The initial y will be 1, and the initial derivative will be also 1. Okay, if we do that, then we see that plugging in for the total, because there is no particular, right? There's no forcing function. So I need my y total of t to be exactly equal to my homogeneous solution, which will be c e to the minus t. And now to specify, you might see where the problem is. I need the total solution at 0 to be 1. So that's c e to the 0. So that tells me that c is 1. Now, we've fully specified c, and there are no more unknowns, but yet, if we try and meet the first derivative initial condition, that has to be 1 as well, but the first derivative of our homogeneous solution is minus c. So this tells me that c has to be minus 1. So this is what we like to call a contradiction. Right, c cannot be both 1 and minus 1, so we have done something wrong. And this is actually kind of a hallmark of this method of undetermined coefficients. But what we have to do is we have to come up with a new guess at the homogeneous solution that also has these properties that we like, that when we take derivatives of that guess, we can get linear combinations that will satisfy this original differential equation. And so the workaround for this, the solution, is to try a different form. So we'll call this c1t e to the minus t plus c2 e to the minus t. We know that the roots are going to be the same, so these powers in the exponents are going to be the same as we had before. They both have to be minus 1 because that was the root that was repeated. But now if I allow for a t times this function, then I'm going to have to do what product rule when I start differentiating this. But once I do product rule, I'll get t times e to the minus t and just e to the minus t's. And those will help me meet both of these conditions. So let's try this same problem again. So I want to do the initial condition, y total at 0, which is going to be y homogeneous at 0. That's going to be 0 times c1 e to the 0 plus c2 e to the 0. So straight away, this is kind of nice. C2 has to be our initial condition 1. And now we've still got one undetermined coefficient, so now we can actually make use of our derivative. So first I'll take the derivative because that's a little more complicated now that we've got this product term. So let's call that c1 e to the minus t minus c1 t e to the minus t. And that was just product rule on this first term. And then minus c2 e to the minus t. Okay, so now the initial derivative, we're set to 1. So we're going to go c1 e to the 0 minus c1 times 0 e to the 0 minus c2 e to the 0. So this all tells me that, what is it, c1 minus c2 has to be 1. And we know c2 is already 1, so c1 is 2. Okay, so now we are able to check our solution. So if the total solution is c1, so 2t e to the minus t, plus 1 e to the minus t. And now we can't combine these anymore because of this t term. So let's check our work. Does this meet the differential equation? Does it satisfy the homogeneous part? So let's differentiate this. So we'll use product rule again. We'll get 2 e to the minus t minus 2t e to the minus t minus e to the minus t. And now we'll differentiate that again, double prime. So here we get minus 2 e to the minus t, and again product rule, so minus 2 e to the minus t plus 2t e to the minus t plus e to the minus t. And now the homogeneous, so let me get a different color to help you out. The original differential equation says take 1 of the double derivatives, take 2 of the single derivatives, and take 1 of these. So I'm going to take that linear combination, and if we do that on the left, the differential equation says we should get 0. So I'm going to change this 2 to a 4, I'm going to change this minus 2 to a minus 4, and I'm going to change this minus 1 to a minus 2. That's the 2 here. And if we try to track down all of the t e to the minus t's, let's do that here. I've got 2 from this one, and what, a minus 4 from this one, and a minus, or a plus 2 here. So that was plus 4 minus 4, so that's 0 t e to the minus t's. And then the only other kinds of terms I'll have are e to the minus t's. So there's a plus 1 here, there's a plus 4, so it's net 5. Minus 2 is net 3, minus 2 is net 1, minus 2 is net negative 1, plus 1 is net 0. So it does check out that this, this guess does indeed meet the original differential equation requirements, provided we have these coefficients in front. Okay, and we already did check the initial conditions. That's how we got C1 and C2 in the first place. So here we go. Here's our final answer. The total solution to this differential equation has e to the minus t, which you would expect when you have a root of negative 1. And it also has 2 t's e to the minus t. And this is a hallmark of this kind of repeated root case, is that you'll need to add powers of t, however many powers you have repeated here. So for example, if you had so a characteristic polynomial that looked like lambda plus 1 to the 3, that would tell me that my homogeneous attempt would have to be c1 e to the minus t plus c2 t e to the minus t. But because I've got a power 3 here, I've got a triply repeated characteristic root, I'd have to go and add another power of t. Okay? So and this pattern continues. It doesn't have to be a root of negative 1, but I'm just using this for an example. Every time you have a repeated root, you will need to use the original exponential with that root in the exponent, and then you need to add powers of t, or polynomials in t, up to the multiplicity of that root. Okay, thanks everyone.